So my name is John Mattox. I am giving a presentation on Megastore. Megastore is a highly scalable, highly available data storage system specifically designed for interactive web services. So what motivated the development of Megastore? Megastore was designed to fuel the data storage system for the new era of interactive online services, things like Google Documents or Google Earth. At the time that Megastore was developed, there was no suitable data storage system for those services, and this motivated Google to develop a new kind of data storage system. But before they started developing this new kind of data storage system, they had to create a list of requirements, things that Megastore could accomplish that would satisfy this new era of applications that were being developed. The list of requirements includes things like highly scalable. Because Megastore is designed to support a very large number of services, Google Documents, Google Earth, all those things, support millions of users all across the planet. The storage system that fuels those services needs to be highly scalable. Traditional databases such as relational databases and MySQL, they're very good, they're very powerful, they're very well understood, they've been around for a long time, but they don't scale well. The developers of Megastore had this from personal experience. One of our previous presenters gave an example from their personal experience of relational databases. Once you get up to millions of users, just don't scale well. So Megastore needs to be a different kind of storage system that could scale up to millions of users. Megastore also needed to support rapid development because every year we hear about some new internet application that's going to revolutionize some facet of life. Megastore needs to be able to keep up with that pace of development. If a new system is developed every year, that means Megastore needs to be developed within a year. If it takes 5 years to develop the data storage system for a particular application, that's just too long. Your competitors are going to overtake you, and that's just too long. So Megastore needs to be simple and quick to develop. Megastore also needs to support low latency. If you got Google Documents and you're typing in, and every time you hit a key, it takes 5 seconds for the server to respond and your changes to be reflected on your web browser, well, that's just unacceptable. One keystroke every 5 seconds. So Megastore needs to support a very low latency. It also needs to support a consistent view of the data. So again, if you're doing with Google Documents and you hit the save button and the document that gets saved looks different than the document that you try to save, well, that's inconsistent. So Megastore needs to be consistent from the viewpoint of the user. So it needs to have user consistency. Megastore also needs to be highly available. Going with the Google Documents example again, if you go to write a document or look at a document and Google Documents is unavailable, you either can't do your work or you're going to find a competitor and use some other service that's lost money, that's lost clients, that's just bad for business. So Megastore needs to have high availability and high uptime. Very closely related to that is fault tolerance. Because Megastore needs to have high availability and because Megastore is going to be distributed across many, many different servers, which are perhaps and even probably going to be physically separated, there's going to be a lot of different components used in Megastore. There's going to be a lot of hardware, there's going to be a lot of networking infrastructure, there's just going to be a lot of infrastructure in general, and because there's a lot of components, there's going to be a lot of failures, and Megastore needs to be tolerant of those failures. So this provides a problem for Megastore. Many of these requirements conflict with each other. The traditional relational databases give you a very strong API, a very strong query language, but they scale very poorly. On the opposite end of the spectrum, NoSQL scales very well, but has very limited API. The queries that you can perform are very simple, very basic, very weak, and it also has a very loose consistency models. And it goes beyond just traditional data stores as well. Traditional methods of fault tolerance include things like replication, which while they do increase fault tolerance, it provides many other problems. It reduces response time, so it increases latency. It makes consistency more difficult. And so there needed to be something new, some new way of storing data in order to solve all these problems. So this is where Megastore comes into play. Megastore attempts to bridge the gap between a relational database and NoSQL, combining the advantages of both of them. It does this by using a synchronous replication technique. This allows it to achieve high availability and highly consistent view of the data, but it also allows for ACID transactions or ACID semantics. Now, ACID stands for atomic, consistent, isolated, and durable. We're not going to go into the details of what those mean and the implications of them because that's really more of a database sort of a question, and we're focusing on distributed computing. But suffice it to say, they're highly desirable qualities when dealing with transactions of any sorts. They these properties are highly desirable, but they also tend to come with steep costs. Things like increased latency times or things of that sort. But Megastore is able to provide a combination of the two. It's able to provide highly available and consistent data while also allowing for ACID semantics. It does this by combining the advantages of NoSQL and relational databases. How do you combine these two opposite techniques? Well, it does this by partitioning data. It takes your entire data set and partitions it into smaller groups of data. Data inside of a partition can be accessed using ACID transactions. That is, transactions very similar to a traditional relational database, giving you a relatively high-powered query language with all the advantages that ACID brings. But communication between different partitions is provided by a NoSQL database. This gives you the flexibility and the scalability of a NoSQL database while still having some of the advantages of a traditional relational database. Now this was deemed this isn't perfect. You can't is not the entire data store can't be accessed using a relational database. And you can't take you there's a limit to how much you can divide your data down. So there's a limit to how much NoSQL like functionality you get. But the writers of Megastore said that most internet-based applications can be divided into very discrete partitions that serve specific functions or give store certain kinds of data, and that for the most part, most of your average transactions with this particular set of data from a particular application will use a single partition. And so most of your interactions with a data store will be with a single partition and give you all of the advantages of a relational database. But the entire data set can still be partitioned and replicated across many different servers, giving you the scalability of a NoSQL database. So how does Megastore do this? How does it provide these opposite qualities? How does it do this miraculous task of combining East and West together into one system that actually works? Well, one of its secret tools is the use of Paxos. Now, Paxos has been used by many other systems before, and it's used in Megastore in a very similar way. It's used for master election, it's used for the replication of metadata, and that's nothing new. There have been hundreds of other systems that use Paxos for that. What makes Megastore unique is that Paxos also uses Megastore also uses Paxos for the replication of primary data. Now, according to the writers of this paper, Megastore is the biggest system to ever use Paxos for the replication of primary data. That means they're kind of a trailblazer in this regard. They're doing something that had never really been done before. Why did they choose to use Paxos? Well, Paxos has a lot of advantages. Specifically, Paxos had been used by Google for many years before Megastore was even developed. So Google well understood Paxos and how it worked. Paxos can support large numbers of reads and writes daily, and it can also support petabytes of primary data stored. So because Paxos can support that, Megastore can support that. Now, they don't use Paxos like it was originally presented or like we covered in class. They actually use a slightly modified version of it that we'll talk about later. But the fundamental idea is exactly the same. So if you want to know how Paxos works, go back and review the professor's lectures on it because I'm not going to go into details of it. But suffice it to say, even though it is slightly different, the fundamental ideas are basically the same. So replication and fault tolerance are given to Megastore by the use of Paxos, but what about some of the other qualities that Megastore needed? How is availability and scalability addressed in Megastore? Well, availability is given to Megastore by the use of a synchronous, fault-tolerant log replicator. That is, because it's synchronous, all other systems that are in communication with this will receive the same data at the same time. It's fault tolerant so that even if a system fails or a packet is lost, it's still able to recover from that. Scalability is provided by the partitioning of data into small databases. If you can take a large data store, break it up into small chunks, and then break these small chunks up over large number of servers scattered perhaps over a single data center or scattered over multiple data centers, that's fundamentally how you scale large data stores across across disparate areas. You take a large data store, you break it up into small data stores. Each of these small data stores has its own separate log that keeps track of everything that happens to it, and all this is stored in a NoSQL data store. As we talked about earlier, NoSQL is one of its primary functions is high scalability. So NoSQL gives us a way of organizing data and across disparate servers, but it doesn't talk to us about how we make those replications across the servers. So Megastore looked at three different techniques for data replication, and it ended up not choosing any of them. It instead chose to invent its own method. So following along with their example, I'll talk about the three different techniques they looked at, and why they were not chosen by Megastore. Why Megastore chose to develop a different and pretty unique solution to its replication problems. So the first replication technique is the use of an asynchronous master-slave relationship. In this situation, a master has a log of some data. There's been a change made to it, and this change needs to be distributed to the slaves. So the master sends the log that has been changed out to all the different slaves. It sends them at the same time, sends this information in parallel. So even though the data is sent in parallel, it's not received in parallel. So it's sent at the same time, but it's not received at the same time. This allows for very quick and acidic transmission transactions, but it has some problems. The first problem is that you risk data loss. If some of the data is lost in transit and the slaves that do receive it crash, then you might lose data. Another problem is that, then this is the big one that Megastore stressed, was that the use of a master requires an external consensus protocol. You have to have some way of choosing a master, especially if the master were to go down. You have to have some way of replacing that master. And in traditional asynchronous master-slave relationships, that requires the use of some kind of external master picking protocol. There are many different ones, but they all have the same disadvantage that they require external hardware, external software. They require extra stuff in addition to just the base protocols and the base hardware. This extra stuff is extra time to implement, extra complexity to implement, and it's also it's another thing that can fail. The more stuff you add to a system, that's the more places where it can fail. So asynchronous master slave didn't provide all of the advantages that Megastore needed. Specifically, it failed in the fault tolerance area. So synchronous master-slave relationships, they're very similar. The difference is that when the master sends out a message to the slaves, it sends a message out to all the slaves at the same time. All the slaves eventually receive this message and reply to the master with a message saying that they've accepted the change. Once the master has heard from all of the slaves, then it says, okay, now this data has been committed and everybody can use it. This gives you a very all or nothing view of the data. Either every slave has this new data, or none of the slaves have the new data. The problem with this is the relationship between master and slave is so entwined that you have to have an external system to detect failures. You have to detect if a master has failed and you got to elect a new master. You have to detect if a slave has failed because the master waits for every single slave to respond. If not every slave responds, then even if there's just one slave that doesn't respond, then the whole system waits. So you have to have an external system to detect failures of the master, failure of the slave. And just like in the asynchronous systems, this requires external hardware. It requires extra hardware that can fail. So this has the problem of also not being fault tolerant. A different technique that is fault tolerant is called optimistic replication. In this case, any member can create a change or a mutation. These mutations are then sent to every other member in the group, and they're sent asynchronously. This means that you've got good fault tolerance because the data is sent out. You have good uh, you have good latency, you have good availability, but you have one big problem. And one big problem is that because you don't know the order that these mutations are going to arrive at different servers, you don't know the ordering of that server's log. So that means one of the things with transactions is that you can undo a partial transaction. You can't undo these changes because you don't know the ordering of it. So because you don't know the ordering, transactions are not possible. Because transactions are not possible, ACID transactions are not possible. So optimistic replication is fast and it's reliable, but it's not, you can't perform transactions with it. So because of that, Megastore also rejected optimistic replication as a possible replication strategy. So how does Megastore actually replicate its data? What is the technique that it uses? It uses Paxos. Paxos overcomes many of the problems that the other ones have. Specifically, it does this by removing the need for a master. Removing the need for a master and instead using a consensus algorithm means that you don't have the single point of failure and you don't have the same kind of communication between masters and slaves. As a matter of fact, in Paxos, you don't even have masters and slaves. You instead have peers. This has some advantages. One is that it's very fault tolerant because if a single peer dies, all the other peers are more or less exactly the same. So you don't have the single point of failure, and even if once one peer dies, all the other ones can pick up the slack on it. So long as the majority of peers survive, the entire system continues. Another advantage is that Paxos is proven. It's not just something theoretical. It's been used by hundreds of different algorithms and across various applications. It's never been used to the scale that Megastore uses it, but it has been very widely used. So it's not just a theoretical idea, it's very well proven. But how does Paxos work? What are the details of it? Now, I'm not going to go into great detail about it. It's already been covered in our lecture, and it's covered in much greater detail than I can cover in my presentation. So if you want to know the details of Paxos, go watch the professor's lecture on it. Instead, I'll just give you the important things of what it does while ignoring the how it does it. So the first thing is that the logs are replicated over a group of peers. These are symmetric peers. That just means that all the peers are the same. You don't have master peers and slave peers. It's just peers. Everybody's the same. That means that you don't have to detect the failure of a master. You don't have to have a master election protocols. You just have peers. The another advantage of having peers is because everybody's the same means everybody can create reads and writes. It means it doesn't matter which node or which server you connect to, you can do reads and writes from it. Log appends, which those are the creation of new transactions, they cause a block until the majority of peers accept it. So when we talked about the synchronous master slaves, the master would send out a message to all the peers or all the slaves, and it would block until all the peers responded. Paxos sends out a message to all the peers, and it blocks until the majority of the peers respond. It means that, again, a single slave failure doesn't cause the whole system to stop. You can have the majority, or so long as the majority of your peers are working and communicating, the system will keep working. It also is very fault tolerant because if a system crashes and then recovers, this system will be in a catch up state. It'll have data it's missing. It'll be behind, but it can catch up automatically. The final thing is again related to the consensus. Because the consensus removes the master and the slave relationship, you don't have the single point of failure if the master fails or if a slave doesn't respond. That means that you don't have to really worry about, did this system fail? Is it still working? I just haven't received this message yet. It means if you look at the state diagram of the system, you can remove the failed state. This removes complexity of the system, which increases the simplicity of the system, which makes it less likely to crash, increasing availability, and all the good things that come with a more robust, more simplified system. Before we continue, we need to talk about partitioning. We've been using the word partitioning a lot, but I haven't really said what it is. I've relied on your intuitive understanding of partitioning based on past experience with things like network partitioning or hard disk partitioning. And that's been good enough, but we need to go into more detail about it. We need to know what is partitioning. We need to know how do you partition the data. We need to know why do you partition the data. We'll start off with that first, with the why first. Why do we bother partitioning our data at all? The goal of partitioning your data is to give the user control, specifically give the user finer grained control than what they would have with non-partitioned data. Now why? Why do we do that? What does fine grained control of data give us? It gives us the ability to control or influence the locality of our data. Now, just like network locality or cache locality or memory locality can greatly increase the performance or hinder the performance of your system, so can locality and Megastore affect the performance of Megastore. That is to say, a Megastore that has good partitioning, and high locality can have much, much better performance than a Megastore with poor partitioning and poor locality. So continuing on with this, we need to introduce some more terminology. Megastore introduces this word called an entity, and also introduces entity groups. An entity group is, not surprisingly, a collection of entities. But what is an entity? Well, first let's make a comparison to traditional relational databases. In traditional relational database, you have rows. Rows are collected into tables, and tables are collected into a database. In Megastore, you have entities. Entities are collected into entity groups. Entity groups are collected into partitions. Partitions are part of your entire data set. So entities can be thought of as the fundamental unit of a Megastore record. But what is an entity? Well, again, we're going to compare it to a traditional relational database. So in a traditional relational database, you might have an entity called John Smith. With John Smith, he might have a name, an address, and a salary. Let's say an employee of a company. This data would be stored across three tables. You would have the employee table, which stores his name, the address table, which stores his address, and the salary table, which stores his salary. So in order to get all the information about the entity John Smith, you would have to query these three different tables. Well, in Megastore, you don't have those three different tables. All the information about the entity John Smith is stored in a single thing or a single row. This thing or row is called an entity. So you have the John Smith entity, which contains his name, his address, his salary, everything else related about it. That's what an entity is. And then an entity group is a collection of individual entities. Entity groups are combined together to create partitions. These partitions are replicated, and then they are distributed over a wide area, specifically a geographically wide area. You do this for two reasons. You want to distribute your applications over a wide area so that you increase your locality. By spreading copies of your data around to geographically distinct areas, you decrease the average distance between your average user and the nearest copy of that data. It also helps to improve the fault tolerant, not the availability of your system by reducing the likelihood of all of your copied data being in a failed state. For example, if all of your data is in a single data center and that data center experiences a network outage, then you've got 100% data failure. But if you've got it distributed over multiple data centers, then the likelihood of a particular entity being inaccessible is much, much less. And then each of these partitions inside of a single data center are stored inside of a NoSQL data store. Now, we'll talk about the implications of that in just a moment. But first, let's talk about what happens inside of a single partition. When a single partition and an entity group or entities inside that entity group need to communicate with each other, or when the server that contains that entity group needs to communicate with the entity group, it does so via a single phase ACID transaction. Now, in a traditional relational database, they use what's known as a two-phase commit, and this is very similar to a two-phase handshake in networking. It gives you all the things that that does. It gives you the ability to confirm, to send a message, to confirm that the message has been sent, to confirm that the message has been received. It gives you all of those transmission assurances that two-phase commit would give you in traditional networking. Uh, Megastore, however, uses single phase transactions. Now that has some advantages and some disadvantages. The primary disadvantage, or the primary advantage, is that you're using half as many messages because you're using only a single phase instead of two phase. So your network traffic overhead has been cut in half. Some of the disadvantages is that you're more likely to lose data in transit. However, the developers of Megastore said that that was acceptable loss because Paxos is used to replicate data, to replicate records and logs across the servers. That means that the odds of losing in transit is very, very small. So the amount of the cost of losing a packet in transit is very small compared to the amount of overhead saved by reducing the amount of phases. But there's more to entity groups than just how they communicate across each other. There's also how does an entity group communicate with another entity group. That's done via the sending and these things called sending entities and receiving entities. These entities, these sending entities and receiving entities, can be thought of as ports or services on a regular computer. A sending entity is attached to an entity group and it sits there and it waits until it receives a message or until it needs to send a message out. This message is put into a queue and it's processed on a first come first served basis. When the sending entity has the availability, it sends the message out to whoever the target audience is. Likewise, receiving entities, they're attached to an entity group and they sit there and they listen. They listen until a message comes in. The messages are put into a queue. They are consumed in a first come, first serve order. And then once the message is consumed, whatever the content of the message is applied. Normally, it's a mutation request to the data stored in that entity group. Now, these sending and receiving entities are very, very similar to the channels that we used in Go, the sending channels and the receiving channels. So we should be fairly familiar with these. Now, back to the idea of how do entities communicate across partitions. When you're inside of a partition, you get to use this single phase ACID transaction. It's very quick and it's very, very efficient. But across partitions, you have to instead use asynchronous messages. Now, this is what really highlights the need for good partitioning. Good partitions increase locality, which allows you to use ACID transmissions more often than not. Whereas poor partitions decrease locality, meaning that you have to send messages across replicas, which means that you have to use this asynchronous messaging. Not only is that slower, it also means that you're using NoSQL, which gives you reduced consistency guarantees. It's everything that you don't want in a Megastore storage. So partitioning is really important, but how do you know where to partition your data at? If it's so important to choose good partitions, how do you choose a good partition? Well, that's actually pretty complex, and it's actually more of an art form than it is science. And that gives me to one of my personal opinions about this. One of the biggest problems with Megastore is that there's no good way of knowing how to partition your data. You have to study your data and study your expected usage patterns and make your best guess at it. And that means that it's very possible to make bad decisions, to make poor partitions, and get really poor performance. For example, we might, going back to our John Smith, the employee example, we might find that we use John Smith's name and his address a lot, but we don't use his payroll a lot. So we would create a partition that contains his name and address, and a different partition that somewhere else that contains his salary information. Okay, so that's good, but what happens if we send our data off to accounting? Accounting is probably going to use his payroll account as payroll data a lot. That means that your original partition, which was fine, is now worthless because now you're accessing two partitions and you're getting all those bad things that we had with cross-partition communication. You've got no SQL communications, and you've got communication across possibly large regions, so you've got extra latency, you've got reduced consistency guarantees. All these things highlight the need for good partitioning and also highlights my personal frustration with this in that there's no way of guaranteeing or even assuring ourselves that we've got a good partition. The best you can do is the best you can do and hope it works. If it doesn't, then you got to try again. So we've talked about what partitions are. We've talked about how to partition data. We've talked about why you partition data. But once the data has been partitioned, how is it stored? What's the fundamental storage unit of Megastore? Well, that's Bigtable. We've already had a presentation on Bigtable, and it was a fine presentation. So I'm not going to repeat all the details about what Bigtable is and how it works. Instead, I'm just going to say Megastore uses Bigtable to store data. And if you want to know the details of it, then go watch the Bigtable presentation. But so why do we use Bigtable as a fundamental storage technique? Well, a couple of reasons why. The first one is both Megastore and Bigtable were developed by Google. So I think that Megastore developers use Bigtable because they were familiar with Bigtable, because they're both Google products. But even outside of that, Bigtable brings some good advantages to the table. Bigtable is scalable. Bigtable has fault-tolerant storage. And you can minimize latency in Bigtable by controlling the placement of data. So again, this goes back to that whole idea of locality. If you can place your data physically near to your users, then you can reduce latency. Another thing is that in practice, Megastore tends to replicate its data 3 or 4 times. That is, for every what I'll briefly call a master copy, there are 3 or 4 other copies of data out there. If you can take these copies of data and get them physically close to your users, then you can reduce latency. So Megastore with Bigtable provides a scalable, fault-tolerant, low-latency data storage system, which is half of the requirements that Bigtable set out to solve, or that Megastore set out to solve right at the beginning of the paper. It's solved right there just by using Bigtable. So how do you interact with Megastore? What's the API for interacting with it? Well, when Megastore set out to create an API for the system, they had a fundamental goal in mind. They wanted a cost-transparent API. And what does that mean? A cost-transparent API. That is, they wanted you to have an intuitive understanding of the cost to perform a particular transaction. If something looks like it should be expensive, then it would be expensive. If something looks cheap, then it is cheap. This is in contrast to traditional relational databases. In traditional relational databases, you would create an SQL statement, for example. This SQL statement is very easy to reason out the correctness of it. Does this query do what you want it to do? But it's very difficult to figure out how long it will take the database to perform it. You might have some very short and simple looking queries that are actually really, really expensive, and other very long and complex queries that are actually really, really cheap. So in that regard, most SQL queries are not cost transparent. Their correctness is transparent. Megastore wanted something that was cost transparent. If it looks quick, it should be quick. Now, in order to build that sort of API, there was some things that they noticed and some qualities or characteristics that that need to be taken into account. The first one is that Megastore is designed to work with high volume workloads when there's a large number of requests coming in and out of the server, coming in and out of the entire service. So and they found that high volume workloads would rather have predictable performance versus robust performance. What do we mean by robust performance? We mean a wide variety of options, lots of different joins, lots of different queries, lots of different ways of selecting data, things like that. They found that it's better if you can reduce your instruction set to a smaller but stable instruction set versus a very large and unstable instruction set. They also found that in their applications, read dominate writes by about 10 to 1. For every one write, there are 10 reads. So they do a lot of reading. They also noted that Bigtable allows you to store hierarchical data. That's not normally that's something that's difficult to do in relational databases. That can be a little bit tricky, but Bigtable allows you to store hierarchical data in a very straightforward manner. So, with all that in mind, Megastore created their own custom schema and their custom data model. This data model was designed to increase the control that you had in order to maximize locality. We talked about how partitioning data was important in order to increase locality, which was a fundamental aspect of Megastore's performance. Likewise, the schema and the data model are also designed to maximize locality. The schema is also designed to make use of hierarchical data. Because Megastore can accept hierarchical data, they wanted Megastore to also be able to use hierarchical data, so the custom schema has to make use of hierarchical data. Another thing was they needed to denormalize data. Now I'm going to talk about this for a little bit because if you're coming from a traditional database background, this is counterintuitive. Why do you want to denormalize data? Well, first, a very brief little introduction into what normalizing is, because you can spend entire classes talking about how to normalize databases, and I'm going to spend a couple of minutes talking about it. But fundamentally, data normalization is taking a database and making its data more accurate and less ambiguous. This is primarily done by taking a large table and breaking it up into multiple smaller tables. As you break the table up in certain ways, you get more and more accurate and less ambiguous data. The more accurate it is, the higher the normal form that you get. So there's first normal form, second normal form, third normal form, up to fifth normal form, and then there are also special normal forms like the Boyce card normal form and so on. Well, one of the costs of increasing normalization, when you increase normalization, you get more accurate and less ambiguous data. However, you get more tables, which means that in order to get every piece of information about an entity, you have to use more joins, and joins are expensive. We've already talked about how Megastore wants to reduce the number of joins in order to get you a faster, more reliable query language versus one that's powerful. So by denormalizing your data, that is putting all records into fewer number of tables, you get a more robust, not necessarily more robust, but you get a more predictable data language. This is entirely about reducing the number of joins needed in your application. Now, Megastore, you can still use joins in Megastore, and sometimes you have to, but join is not provided as a fundamental command. Instead, you have to do that in your application. You would have to download two tables and then join them in your application manually. So what does a Megastore schema actually look like? We'll talk about that in the next slide, but before we actually show it, we'll talk about some characteristics or properties that the Megastore schema has. First, Megastore schema is a strongly typed language, a strongly typed schema. That's just like a strongly typed language in programming. That is, you have to explicitly say the data type when you create your variable. Uh, just like in traditional relational databases, you have tables, and tables are a collection of entities. That is to say, a table and an entity group are more or less the same thing. Each entity has properties. These properties are very similar to the columns in a traditional database. You might have the employees table, which have the properties of name, address, or salary, or things of that sort. And since each of these have a specific data type, we'll talk about the data types. There are three data types. There are strings, there are numbers, and then is the Google Protocol Buffer. Now, it's actually a little bit more deep than that because there are a couple different types of strings, there are several different types of numbers, but fundamentally you only get three types of data. There are strings, there are numbers, and there's a Google Protocol Buffer. Now, I'm not going to talk about what the Google Protocol Buffer is because that's not what we hear about, but we know what strings and numbers are, and we can see there's a relatively limited type of uh, type of data that can be stored. So if you want to store something like a date in SQL, there's a date data type, but there is no date data type here. You have to use either a string or a number and make your date fit using a string or a number. One other quality that the schema provides is that properties are used to form a primary key. Just like in relational databases, every table has every entity has to be uniquely identifiable. It has to be uniquely identifiable by a primary key, and this is another data model. Megastore is just a type of data model. So every entity has to be uniquely identified by a primary key. These primary keys are formed from one or more properties. So we'll look at that at now. Here's a simple example of a Megastore schema. Now I'll go into greater detail about all the different components of this, but for now we'll just look at the general idea of it. We can see it looks very similar to SQL commands. Here we've got a create table command for a user. This creates a table. This creates a table called user. That's just like an SQL. And then we can see here are the different properties that are created. There's an user ID, it's an int64, and here's a name, it's composed of a string. We also see that every table has a primary key associated with it. Each primary key is composed of one or more properties from the table. Here's a bigger table. This is a photo table. He's got user ID and photo ID. Those are an int64 and an int32. Here's a thumbnail URL. It's a string. And its primary key is a composite key composed of the user ID and the photo ID. And we see that there are some other things that we'll talk about. For example, there are instances that we'll talk about. There's these required versus optional versus repeating tags that we'll talk about. But we'll go into more detail of those in just a moment. So we're going to start off talking about indices. Indices are these complex little devils that play a key role in influencing the locality of data. There are two kinds of indices. There are local indices and global indices. Now, local indices, they are maintained by an individual entity group. Each entity group has its own set of local entities. These local these local indices are used to provide atomic and consistent updates of the primary data. That is, they're not used to modify metadata. They're only used to update the primary data. In addition to that, they're also used to find data within an entity group. Find data, how are we finding this data? This data is always going to be local. That means it's always going to be a local read, which gives us the ACID transaction ability. That's what local indices do, is they guarantee a local read. They also give us a high consistency guarantee. This is in contrast to global indices. Now, global indices, they span entire entity groups. So a local index is maintained per entity group, whereas the global indices can span entity groups. When they're used to find data from entity groups when you don't know which entity group maintains the data. So remember that you can have, maybe you've got John Smith and George Smith and many of these other people. They're all their information is stored in a single entity, but different entities could be stored in different entity groups. You might have the Smiths stored in one entity group and the Matthews stored in a different entity group. And so in order to find which entity group contains a specific piece of information, you use a global entity to find that data. Some other things that indices can have is you can have different types of clauses. You can have, for example, a store clause or a repeat clause. Now, I don't have an example of a store clause in in our SQL up here, but we do have an example of a repeat clause. For example, we've got right here this repeated string tag. What this does, the repeat clause gives us access to the hierarchical data. In practice, these repeated properties look like comma separated values. For example, if you had a record, a photo record, let's say it was from user ID 1, photo ID 1, that's our primary key. The tag would be a set of comma separated values. It might have family, comma, vacation, comma, Europe. In a normal database, this would have to be separated into a separate database. You would have the tags database, and which would be linked to the photo database by a foreign key. But you don't do that in Megastore. Instead, you use the repeated key to give ourselves access to hierarchical data. So we know that fundamentally all data has to be stored in a big table. So we have to somehow be able to take the data from that schema in the previous slides and map it to Bigtable. And we know that Bigtable is formed by the intersection of columns and rows. So we have to be able to identify Bigtable columns and Bigtable rows. So what is stored in a Bigtable column and a Bigtable row? Well, Bigtable column is created by taking the Megastore table and concatenating it with the property. So for example, we would have photo concatenated with user ID. This would get us the string photo user ID. That concatenation gets us the Bigtable column name. This was chosen because this allows different entities to be mapped into the same row without collision by taking it forces each entry to be unique. Bigtable rows, however, they primarily store the metadata for the entity group. What this does, it lets you create atomic updates through a single Bigtable transaction. That is, you can update your metadata through a single transaction as opposed to having to making multiple smaller transactions. How do indices relate to Bigtable? How are they stored? Indices, which you can be thought of as like a separate or smaller little database, they are stored in Bigtable and it's a single Bigtable row. So each entry in this index is stored as a single row in Bigtable. The row key is identified by the index properties. In this case, we've got the properties of user ID and time, as well as the primary key of the index entry of photo, which the primary key of our photo table is user ID, photo ID. So this gives us the tuple user ID, which is one of the properties of the index, time, the other index of properties, and the primary key of this table. Now, with all that out of the way, we can start talking about how transactions actually performed on this database. What is the process that does it? First thing to remember, and I'm going to bring this up several more times throughout this presentation, is keep in mind that Megastore entities are basically miniature little databases because they have access to ACID semantics. That's important because that's why we're doing all this work. All this fuss and muss is so that we can give ACID semantics or ACID transactions while still maintaining the replicability of NoSQL databases. So what's the first step of a transaction? Everything's got to begin somewhere. Transactions begin by writing to the log. Each entity group has a log. Data mutations are written to the log. Once the data has been written to the log, the mutations are actually then applied to the data. Some other things to keep in mind is that Bigtable, because of just because of all that Bigtable is, allows us to store multiple values in the same row and column, so long as they have different timestamps. That means that really each row column pair can be thought of as three-dimensional. There's an X, there's a Y, and there's a Z. There's the row, there's a column, and then there's the time. So this allows you to have multiple versions of a single entity in that same location, that same row column pair. When you do a read action, the read action by default uses the most recent completed transaction. That is to say, the transaction or the timestamp with the highest value. So because Megastore uses Bigtable, and because Bigtable has this notion of timestamping, that means that reads and writes don't need to block each other because reads are going to read the most recent timestamp and writes are going to write to the next timestamp, or a later timestamp at least. So reads and writes don't block each other. That's a pretty big advantage. We also have multiple types of reads that we can talk about. Megastore supports three types of reads: the current read, the snapshot read, and the inconsistent read. The current read is the biggest or the most powerful or the slowest sort of read. It's your default one. It's performed within a single entity group, and it works by this. First thing it does is it ensures that all writes that have been committed are actually finished. That is, everything that's been written to the log has actually been applied to the data. So it makes sure that everything is as recent as it possibly can be. Then it just finds the timestamp with the highest value and reads that. What this does is it means it gets the most recent version of all the known data, even the data that hasn't been fully committed yet, because it forces a commit to occur. So it commits all the data and then reads it. The next type of read is the snapshot read. Again, this is performed and inside of a single entity group, and it works by this way. The entity finds the most recent completed timestamp, and it reads from it. It's just that simple. It's extremely fast because it just finds what's done and it reads. It doesn't wait for any incomplete transactions to finish. It doesn't wait for things that have been written to the log but that have been committed but not yet written. It doesn't wait for any of that. It just, what have you got right now? Give it to me. It's very fast, but it's not the most recent data. The last read type is the inconsistent read type. This one completely ignores the state of the log and just goes and finds the most recent value. It's even quicker than the previous version. It's extremely quick, but there's two problems with it. One, it can produce stale data because it can get data that's old but just hasn't been updated yet. Or if the process is in the server is in the middle of a read, it can actually get partial data. It can read half of a record, which if your if your system is if your system needs a read that quick, then you'd have to be willing to make that sacrifice of possibly getting partial data. That's just an option that the Megastore developers gave you. You can have very accurate reads, you can have moderately quick and moderately accurate reads, or you can have very quick and possibly not that accurate reads. Three types of reads for three types of situations. Now, what about writes? There's only one kind of write, and it's just the write. And writes always begin with a read. They begin with a current read. So that is to say, everything that's previously known has been committed and has been written. Then it gathers all mutations, everything that's already been written but hasn't been committed yet, assigns a timestamp to it, and then appends it to the log. This log is communicated using Paxos. And the concurrency control for this is optimistic. That is to say that multiple writes can be sent to the same log using Paxos, and one of them will win. We don't know which one. It'll be whichever one got there first. So if a write has been issued to the log and there's a write going on at that moment, the write will simply be lost, and the person who initiated the write will have to initiate another write. So there's actually this is something that Megastore can have problems with. If you're doing a large number of writes, you can get a lot of concurrency conflicts. Megastore solves this issue using a couple different techniques. The first one is Megastore isn't designed to support a high number of writes. It's designed to support high number of reads. As a matter of fact, 10 times the number of reads as it does writes. So Megastore officially says that if you're doing one or two writes per second to a given log, you're probably going to be okay. If you're doing more writes than that, then what you need to do is group it all into batches and send multiple batches of writes. A batch is just multiple writes written into a single file. You imagine taking multiple writes and putting them into a zip folder and sending that whole thing across. So that's another possible shortcoming of Megastore is that It doesn't handle multiple writes very well because it uses this optimistic concurrency. So what is the write transactions process? Well, it begins with a read, a current read actually, and it reads all the information and gets the timestamp, the next available timestamp, and the next available log position. Then it reads from Bigtable and gathers all the writes that it knows about into a single log entry. This is then committed to the log using Paxos to append that write to the end of the log. Those mutations, those writes, are then applied to the individual entities and the individual indices. And then there's a cleanup. All the temporary data and everything that was used to support all that is garbage collected. Continuing on with transactions, let's briefly revisit the idea of queues and talk about them in greater detail. One thing to keep in mind is that queues are used to allow entity groups to communicate with each other, and they're used for sending and receiving of atomic messages. Another important facet is that they can provide for synchronous or asynchronous messaging. Now, this is important because it was interesting in how it does it. It does it differently than the way Go performs synchronous and asynchronous messaging. The way that Megastore performs synchronous messaging is if the sending and receiving queue is the same, then it would be asynchronous. That is, it can't send a message until it receives a message, or vice versa. Whereas if you have a separate sending and separate receiving queue, then the messaging is by definition asynchronous. We'll also revisit this idea of two-phase commit. We talked about how Megastore allows for two-phase commit to allow for communications across partitions. But you can also, not across partitions, but across entity groups. But the use of two-phase commit is officially discouraged. The reason being is because queues exist. Queues are faster and they reduce the risk of contention. You can't really contend for a queue because if the sender or the receiver is full, it just gets put in the sending or receiving queue. But two-phase commit is something that Megastore Megastore supports. According to Megastore, it's included primarily for unique applications for which the queues are not appropriate. They didn't give an example of what, so apparently that's for really exceptional or really unique cases. A few other features that Megastore has is Megastore supports the use of various kinds of backups. It supports the periodic full snapshot backups. It also supports incremental snapshot backups of the primary data or uh, incremental snapshot of the transaction logs. These backups are primarily designed uh, to undo programmer mistakes, such as somebody accidentally typing table drop tables or something like that. It's not really designed to undo, oh, I mistyped something, hit Control Z. No, it's designed to recover from monumental failures or to make monumental failures not as monumental. Another interesting thing is Megastore also supports encryption. It can encrypt individual entities or it can encrypt uh, transaction logs, and that each entity group will have a distinct key. So while each entity can be encrypted individually, they share the same key as everything else in that group. So functionally, each entity group can be encrypted, or transaction logs can be encrypted. So now we're going to start talking about some of the real nitty gritty of Megastore. We're going to talk about replication. Before we start talking about it, there are some things that we need to remember that we've already discussed and some things we just got to keep in mind because they're very important. First, replication is done via Paxos. And it's not the original version, it's a slightly modified version that gives lower latency. Some other things that we got to keep in mind when we're doing that is that Megastore is designed to provide a single and consistent view of all the data that's stored as replicas. That consistent view is what motivates everything that we're about to talk about. Some other things to remember is that reads and writes can be initiated from any replica. Any replica can start a read, any replica can start a write, any replica can read or write from another replica. Within an entity group, ACID semantics are provided, and replication is performed by sending a transaction log to a quorum of other replicas. Now, remember quorums from when we talked about Paxos in class. So a replication is performed by sending a log to other replicas, which then use that log to bring themselves up to date. Now, a brief overview of what Paxos is. Paxos is simply a method of reaching consensus amongst replicas. That is, fundamentally it doesn't do anything else but reach a consensus. It can, one of the reasons you use it is because it can handle delayed or reordered messages very well. It can handle messages that arrive late. It can handle messages that arrive out of order. It can handle messages that arrive in order. It's a very robust consensus algorithm. It requires a majority to be active and reachable. That means it can handle a relatively large number of failures, but only up to a certain point. It's basically a little bit less than half of them can be a little bit less than a third of the systems can fail. If you got F that failed, then you need two F still active. So it's about one third of the systems. The original version of Paxos worked by using multiple rounds of communication. That is to say, you would send out just like a two-phase handshake. It required multiple round-trip communications in order to succeed or finish. This was not really suitable for high latency networks, that is, networks with a lot of communication or they had a lot going on in them, like what Megastore has. And here's a brief overview of how the original Paxos worked. You can divide it up into two different components. There's the writes and the reads. The writes require two round trips because you had to send out one round of prepare messages where you told everyone get ready to receive a commit message, and then a round of accept messages where everyone said, "Yep, we got it, everything's good." And reads require at least one round trip communication because you got to read from everybody to figure out what the greatest value is, and then read that one. In the real world, this is a lot. This is a lot of communication. So in order to make Paxos practical, you have to somehow reduce the number of round trips. So in order to do this, you can use a master. You can use a master to reduce the amount of latency involved. Because if you redirect all reads and writes to the master, then the master is always up to date. That means that reads can be issued without any need for consensus. You don't need to contact everybody. You just need to contact the master because he's always got up to date. So, and writes can be done with a single round of network traffic. And this is done by basically smushing the prepare and the accept messages together into a single message. It's it's not as robust as the two round, just like single phase commit versus two phase commit, or single phase handshaking and two phase handshaking and networking. But it saves a lot of traffic, a lot of mex and a lot of it saves you a lot of network traffic and makes this whole system faster. However, using this master comes with problems. One, it reduces flexibility. Now you've got to have a master. We talked about masters earlier and why things like asynchronous master-slave relationships weren't used because of all the problems that having a master brings about. So what are some of the disadvantages that having a master brings us? First, transactions must be performed near the master. Because everything has to go through the master, you want a very small amount of network latency connecting your non-master nodes with your master nodes. Otherwise, if you got a master node on one side of the planet and a servant node on the other side, then it's got to traverse the whole planet to get there. That's a large amount of latency. So they got to be physically located near each other. In addition, masters have to be big. They have to be powerful because they have to do a lot more. They have to handle a lot more communication, a lot more traffic than non-master nodes. So all of your potential master nodes need more resources. It means better hardware, more memory, faster network, better CPU, all that sort of stuff. And and so you've got this list of potential masters that have got this greater than average resources, but those are wasted until the master until they're a master. So when they're just sitting there as a regular node, the 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 resources are wasted. Another problem with masters is that detecting a failed master is complex. You need a complex state machine, and you also need timers. So that all this extra stuff is stuff that's extra hardware, that's extra software, that's extra stuff that you've got to maintain. We talked about earlier how we wanted to avoid all that, but Megastore wasn't able to fully avoid the use of a master. Because base Paxos had such a high network overhead, the only way that Megastore could get around that was to use a master to overcome the high latency of Paxos. So how does Megastore solve this problem? How do they use a master system to overcome the problems of Paxos without using a master system and having all the problems and overhead that a master system has? Well, before we talk about that, we're going to keep in mind some things that Megastore said. There's some guidelines that they set out before they sought to solve this problem. First, they recognized that most reads succeed. Reads are just very simple, and most reads succeed. So therefore, local reads should be allowed because they're probably going to succeed. In addition, they wanted to use this notion of a fast write so that masters use this prepare accept messaging system. That is to say, they wanted to always use, when possible, this single phase Paxos write. This taking these two notions, the notion of the fast reads and this fast single phase write, they was able to, instead of using dedicated masters, they was able to use what Megastore calls leaders. Now leaders, what they are is they're a specific instance of Paxos. They run on a per log position instance. That is, each log position has an instance of Paxos running. Each log position has a leader who is chosen. This leader is a replica, it's just like everybody else. So it's not a master because it doesn't have all of the extra hardware that a master would normally need. But it is a master because it does many of the master jobs. So that's what we're calling a leader. So a log position, each log position, that is, each entry in a log has a leader. This leader was chosen when the log's value was chosen. Now, how's a log value chosen? Remember, this is using Paxos. So per Paxos, it uses consensus to pick in quotation marks a log value. So when the log's value was chosen, a leader was also chosen. This leader can use the proposal 0. Again, I'm not going to go into the details of this, but remember Paxos and remember the importance of the proposal 0. This gives the leader very quick access to the value, whereas other replicas have to use the full two-phase Paxos in order to change that value. Rights, they have to be submitted to the leader before they're submitted to other replicas. So that's very much like the master situation. You don't submit rights out to everybody. You submit rights to the leader or the master, and the master submits those rights out to everybody. That's how you're mimicking the advantages of a master-based system without having the master. The How's a new leader chosen? A new leader is chosen primarily based on the closeness. So if you've got a particular piece of data that you're writing to, the Megastore will try to choose the closest replica to that data store in order to that piece of data and choose that one as the leader. They found that this was effective because most applications tend to write to the same region over and over again. That is to say, you do a lot of looping in computing, and when you're writing, you tend to do a lot of looped writing, where you write either to the same value each time, or you write to the next value over and over again. So this is how Megastore combines the advantages of two disparate things. It combines the advantages of a master-based system with the advantages of a not master-based system by using this pseudo-master system. Since replication is at the heart of Megastore, we've still got more to talk about in replication. One feature or one entity in replication is the coordinator. Each replica has a coordinator attached to it. So for if you got a data center with 5 replicas, each of those replicas has their own coordinator attached to them, and it runs like a service. The primary purpose of the coordinator is to facilitate reads. It does this by tracking every entity group that coordinator has ever that replica has ever seen. Now, it only tracks entity groups which have a complete record with them. That means they're complete. They're not replicas that have fallen behind and need to catch up. But what it does is once it sees them, it keeps track of them, and it can now serve local reads from that group, from any entity group in that set of complete replicas that it's seen. Why does it do this? Why do you have this special piece of hardware attached to every single replica that the only thing it does is read? Well, remember that Megastore is designed to read uh, 10 reads for every write. So it does a lot of reads. And coordinators increase the read speed by making more reads local and by reading faster than you can read from Bigtable. So coordinators, it's extra hardware, it's extra software, it's extra complexity, but it increases read speed. So Megastore uses coordinators to track complete replicas and read from those complete replicas. Now we have multiple replica types. Uh, Now nothing could be as simple as having a single type, so we've got 3 replica types. You've got full replicas. They're exactly what you would expect they are. They're everything you would expect from a replica. They store data, they store primary data, they store metadata, they write logs, they vote, they do everything that a replica should. Then there are witnesses. Witnesses, they're miniature replicas. They don't do everything that a full replica does. They vote in Paxos rounds, and they store some write-ahead data, but that's really it. They don't apply logs, they don't store entity data, that is, they don't store primary data. All they really do is store just enough information that they can be used to, that they can, so they can make an informed vote. They're basically used for tiebreakers when there's not enough people to reach a consensus. You can call on your witnesses to substitute some of those non-responding full replicas. On the opposite side of the spectrum, you've got read-only replicas. They don't vote, but they store full snapshots. All they really are is they're backups. They're backups at a certain time shot, a certain slice of time. That data is backed up to a read-only replica. They're just there for backup. And the last component of replication we're going to talk about is replication servers. Their primary purpose is to reduce the number of round-trip communications needed. Remember when we was talking about Paxos, one of the things that made it inappropriate for general use was the large number of round-trip communications needed. Replication servers help to mitigate that by creating an intermediary between the application that's performing the action and the big table. They also detect and fix failures, failed writes created by a failed server or failed application. They do this just by simply submitting no op values via Paxos to the log record that has the failed write. So here we can see how many of the components that I just talked about relate. In this particular instance, we've got 2 full replicas A and B, as well as a witness replica and replica C. We'll see how this witness replica is important and how it relates to everything else. But first, we'll start off with replica A. We can see that it's performing a write. So it's sending data to its local big table. It's ignoring its own replication server. And we also see that the coordinator is aware of this. The coordinator, because it sees every entity that is complete and this is a complete transaction, the coordinator should be made aware of this. We see that a write message is sent to replica B. It's sent to replica B's replication server. We see that the application server and the Megastore library has nothing to do with this communication. We also see that this write, which is initiated by replica A, does not go straight to replica B's big table. It goes through the replication server first. And we also see that the coordinator is again made aware of these changes because the coordinator is aware of all complete transactions, so complete entities, and this is a complete entity. And finally, we see that a write message is also sent to replica C's replication server. This replication server then writes to its local big table, but if we look at the bottom, we see it writes just the log values. The log data is what's stored in the big table, not the data. This is important because replica C can be much, much smaller than replicas A and B, but it still contains log information. This log information is used for when replica C needs to vote. For example, if replica A tried to do something and it needed a vote, replica A and replica B could easily tie. So replica C, being a witness replica, has the log values it needs to make an informed vote, but it doesn't have the storage overhead of a full replica. So let's talk about the read process in more depth, specifically from a data structures point of view. What is the exact process for a read? Well, the first step is to perform query local. Query local simply accesses the local replica's coordinator and sees if it's up to date. If it is up to date, then everything's wonderful. If not, then it needs to be updated. Once it's updated, the next step it can do is it can perform the find position step. What this does, it finds the highest log value that's been committed and then checks to see if that log value is local. If it is local, they can perform a local read. If it's not local, then it has to do a majority read. And so now it has to query all the other Paxos servers and pick one of those values to read from. You can have it. You have a choice here. You can choose to read the most responsive value, or you can choose to read the most up-to-date value. After you do that, you perform catch-up. This is where you take the local log and you add to it to include the values that you just read. The, if this record, if this log value that you just read has unknown values in it, then you use Paxos to introduce no op writes. Now, we're not going to go into the details of this because you go back to Paxos, but there might be blanks or holes in your log. If there are, then you in the log that you received. If there are, then you use Paxos to introduce no ops. Now, then these no op rights will get submitted to everyone else by a quorum. Everyone else will either give you the correct value and let you replace it, or they'll say, yeah, we don't have the correct value. Go ahead and do a no op there. After that, the next step is to validate. If the local replica was not up to date, then you need to update your coordinator. Now remember, coordinators are really simple, so this validate message is really simple. All it does is it says that the entity replica pair has been committed. It's been saved to the local data store. And it doesn't even wait for a reply. There's no data, there's no error checking. It sends that to the coordinator because the next read will retry all this anyway. If the coordinator is not up to date, then it will try to update it again. The final step is to query the data. Now that you've got all of your bookkeeping done, your coordinator's up to date, presumably your data store's up to date, you've got the correct data, now you can read the data. If something has happened and you've got a failure between the previous step and this step, then you simply try it again. You select a different replica and you repeat the whole process. So revisiting writes, but again from a data structure perspective, what are all the steps that are needed to perform a write? Well, first we need to remember all writes begin with a read. So it means writes have 5 steps and reads have 5 steps. But because all reads begin with a write, writes functionally have 10 steps. They have 5 steps of a read and then 5 steps of a write. Next thing is that reads are used to find the next unused log positions. If you read from log positions 1, 2, and 3, you know that log position 4 must be available because there's nothing there. Or you know that log position 4 should be available. At the same time that you're doing these reads, you also need to choose a leader. Remember that leaders are chosen primarily based on the locality, the location to the data. The closest available replica is chosen as the leader. When the values are committed, all the changes that you want to make, your timestamps, your leader nominations, your values, all that stuff is packaged together and proposed at the commit time. We'll talk about commit once we get to it. But if the commit wins, then it's applied to all of the replicas. That is to say that not just all the replicas that accepted it, but to all the full replicas. Otherwise, if the commit loses, then the transaction is aborted. So the actual steps, after the first 5 steps of read, on your sixth step, or as I'm showing here, the first step, is to accept the leader. You ask the leader to accept your proposed value. If it's successful, then you can skip straight to step 3. Otherwise, you have to go to step 2. Let's assume, for the sake of argument, that the leader did not accept the proposed value initially. So now you have to go to step 2. Step 2, you use Paxos's prepare phase at all replicas that have a higher known proposal number. Remember how Paxos works. We've got different proposals with different proposal numbers. The highest proposal number wins. So you try to find the proposal number with the highest value and then replace your proposal number with that higher proposal number. After you do step 2, you go to step 3 and you ask all of your replicas to accept it. You initiate a vote. If it fails, you go back to step 2. If not, you move on to step 3. You move on to step 4. Step 4 is invalidate. The coordinator at that location no longer has up-to-date information. You have to invalidate it. Step 5 is then to apply these mutations or these changes to as many replicas as you possibly can. Some interesting things about this is the data is committed or durable at step 3. Once the replicas have voted to accept the value is durable. It's in there and you don't have to worry about losing it. But you can't read from the data until step 5. So this brings up an interesting notion. According to step 4, it says that each replica must either accept the value or it must invalidate its own coordinator. This implies that a single replication failure can cause the failure of that entire replica. And that is true. That is absolutely true. A single failed write to a replica can shut the entire replica down. However, the writers of Megastores argue that's not really an issue. The reason being is because coordinators are extremely simple. They are so incredibly simple because they have no external dependencies. There's no external libraries that they rely on. There's no external services. There's not even any persistent storage. They're just a block of RAM and a little CPU. Because of that, they're extremely stable. Because they're extremely stable, the coordinator is rarely the cause of a failure, or rarely ever at fault. They said that network failures can be an issue if you can't contact the coordinator, but that's a whole separate issue. They said that the architecture of of the coordinator in relation to Megastore is very robust and very reliable. So if coordinators are vulnerable to network failures, how do we detect these network failures and how do we recover from them? Well, that's primarily provided by the use of Google Chubby. Google Chubby is a locking service that other papers, one of the previous papers covered this as well, but I'll cover it briefly. The basic idea is that at startup, each process obtains a number of locks. These locks have to be maintained. They're maintained basically by sending a ping to the Google Chubby server saying that I'm still here. If a service loses the majority of its locks, then it reverts to what it called a conservative state. This conservative state is just where it considers all of its own local data to be out of date. This means that the next time it performs a read, it has to do a majority read instead of a local read, which would then update its coordinator to the current state, and it just recovered from the failure. Now this does have some disadvantages. It does waste time because you have to wait for the chubby lock to expire. However, the amount of time wasted is measured in the tens of seconds, and this tens of seconds of waste is considered acceptable by the developers of Megastore because you're only talking about coordinator failures. Because coordinators are very simple, they rarely fail. So you're talking about tens of seconds of failure, which is not very long, every only rarely. This is considered an acceptable trade-off by the developers of Megastore. Now, there are other types of network failures that cause great amounts of consternation and require a fair bit of manual work to overcome. That's what's known as a partitioned network failure. That's where you've got these two replicas. You've got network 1, which contains, amongst others, replica A, and network 2, which contains, amongst others, replica B. Now, you can think of these two networks as being two different data centers. You somehow lose network connectivity between data centers, but replica A still maintains connection to the Chubby service. In this case, the only way for replica B to recover from this is for a user that is the administrator of the Megastore net service to manually go into replica B and tell it replica A is permanently out of commission, at least until further notice. That takes a fair bit of work to do, but this is a very unique sort of network failure that is also very unusual. Coordinators are also vulnerable to race conditions. They have different kinds of messages which can create different race condition scenarios. There are two kinds of messages that coordinators deal with. There are invalidate messages and there are validate messages. Invalidate communication involving invalidate messages are always safe, but communications involving validate messages may be subject to race conditions, but even still, there are some combinations of validate messages that are always safe. For example, a validate message from an earlier write and a later invalidate. So an early write and a late invalidate are always safe. A higher number invalidates always trump lower validates. So this is another safe condition. If your invalidate is higher than your validate, then you're also safe. So really, the only situation that causes a race condition is when you've got a high numbered invalidate and a low number validate. That can create a race condition or crash as they used in Megastore. Now, what is this numbering system I'm talking about? This is the clock systems that we used, or the epoch systems that we talked about in class. That's exactly what we're talking about here. And these crashes are detected by by sensing if there's a validates are only allowed if the epoch number is unchanged since the most recent coordinator read. That is to say, if the coordinator reads something and then the epoch number of that read is different than the current epoch number, then it knows that there must have been a race condition, a conflict and crash in there. Some other final thoughts about coordinators is that we talked about all these different things. Coordinators have race conditions, they have network failures, they've got all these different things, and they just add an extra component that can fail. But why are they worth it? Well, remember, coordinators increase read speed. Reads are 10 times more prevalent than writes. So that extra speed is really valuable. Plus, the failure rates are very small. They're very small because coordinators are ultimately very simple. They're very simply built. The tasks that they perform are very simple. The size and the amount of network traffic they get is very simple. And many failure types are simply detected by Chubby and they're solved very quickly and very efficiently. So this is why the Megastore uses coordinators, even though they add an extra level of complexity and all that, they're worth it because they don't fail very often and they increase your read speed by a noticeable amount. So as we've said throughout this whole presentation, Megastore uses a unique form of Paxos. This unique form of Paxos was created to solve some problems that Megastore needed to solve, but it also created a very unique set of trade-offs. Primarily, these trade-offs are related towards the right aspect of the whole process. Because Megastore is designed handle 10 to 1 writes, that means that it made these trade-offs in the 10 to 1 reads. It made these trade-offs in the write area. An example of that is you can have a single application and it can start multiple writes at the same time, but all of these writes will fail except for one. So if you issue 5 writes, 4 writes will fail and then one will succeed. What happens to the 4? Well, they have to be retried. So now you've got then 4 writes that are issued and 3 of them fail. Then you've got 3 writes that are issued and 2 of them fail, and 2 writes that are issued and one of them fails, and then you finally get your one that succeeds. This is considered an appropriate trade-off by the developers of Megastore because of the extreme read-to-write ratio. But the developers of Megastore did recognize that there still may be times when you do a large amount of writing. And so they've suggested some techniques that you can use to help mitigate this. If you do a large amount of writing and you're doing it in a very specific way, you should be able to use partitioning to help mitigate this. If you're writing to two different partitions, then there's no conflict because each partition is independent of all the others. So if you can partition your data such that writes always occur in different partitions, then you can avoid these conflicts. Another thing you can do is you can use batches of writes submitted in a queue. Now this reduces your maximum penalty of per write, but it does it by increasing your average minimum. Now this overall, if you're doing a large number of writes at once, this will give you an overall performance increase. But for what we'll call random writes, it will increase that penalty. So it's not always an appropriate solution. And then the last solution that was suggested by the developers of Megastore is that you simply manually control your writes. If you just pause your writes or make it so that you're never writing to two replicas at the same time, then you can't have a conflict. It's kind of a cop-out solution if you ask me, but certainly a valid solution. And the last part of this presentation is the Megastore developers' experience with this. Some things when they was started to develop this was they wanted to develop it in a way that was testable. They wanted testability to be foremost amongst their development techniques. So they focused on writing many cheap assertions. These assertions were very quick to write and very quick to run, but there was a lot of them. This gave them a very high amount of unit coverage in their testing. Another thing that they used, and I thought this was interesting, was they used a network simulator. What this network simulator was, it created a set of pseudo-random tests that was performed on their network. And it tested possible orderings, possible delays, and did it in a random fashion. And it also did it deterministically. So if you found a particular combination that was problematic, you could replay it over and over again, make tweaks to it, and figure out exactly why that combinations of orderings and delays and what have you caused issues. They said what they would do is they would write these tests and then they'd run them overnight, and the next day they would come back and look at it, and they said they found many interesting problems, things that they would never have expected or tested on their own. And this doesn't test all possible combinations of orderings and delays and packets and what have you, but it does test a very large number of them, and they said it tested very unique combinations that they never would have thought of on their own. Some other things that they noted is after they developed Megastore and deployed it out in the real world, is that the everything matched what they expected. The majority of reads were local, just like they expected. The number of reads to writes was about 10 to 1, just like they expected. They found that writes cost about one round trip worth of time, which that matches up with the Paxos version that they developed. They determined that writes, which normally would take two round trips, actually take one. And they said that most applications that use this actually use the provided schema language. The people who use Megastore didn't feel the need to make additions to it. They did say that their own Google App Engine created a language on top of their language, but that was the only one that they know of that has created their own custom schema on top of the Megastore schema. Another thing they found was in their development that a lot of times when people talk about high availability, they really don't mean about fixing problems, they mean about masking the problems. So you don't actually have high availability, but you have the appearance of high availability. They found that when they were developing this, that fundamental faults should really absolutely be fixed and not masked. They said that fundamental faults need fixed as soon as they're discovered. It sounds like a pretty basic thing, and you hear that in your computer science 101 classes. Fix problems, don't cover them up. But it was interesting to hear that even Google had the exact same problem. They wanted to just band-aid fix problems instead of really addressing it, and that caused them problems when they were developing Megastore. And the last thing that was interesting was they found that complex queries can become really slow. That's pretty obvious, but they said that the slowness increases exponentially with the complexity. That means it can be really a really complex query can be really time consuming, and this presents a fundamental problem because fixing these queries requires a fundamental knowledge of Bigtable. So you can't just know Bigtable, you can't just know Megastore in order to fix these complex queries. You have to know Megastore, you have to know Bigtable, you have to know everything about Bigtable in order to fix these fundamental problems in these complex queries. This means that there's a very high skill ceiling when it comes to using Megastore and Bigtable. All right, that's my presentation. I hope it was informative.